Right. So before the break, we look at what is shearing stress. Okay. So you know the labeling convention of the shearing stress now. You know what does shear XY actually mean and what does shear YX actually means now. Okay. Important thing that I want you all to remember is the state of equilibrium. Okay. Shear XY is equal to shear YX. I want you to remember. Why? Because what I'm going to do next, okay, will be influenced by the state of equilibrium. Okay. So let's look at the failure. Okay, failure by shear deformation. Okay, let's look at failure by shear deformation. Okay. So, oh God, sorry. So I'd like to highlight this, right? The shear deformation. The shear deformation is due to the shear force, which we will call V. Right? You're in 2P04, you'll do shear force and bending moment diagram. Yes or no? Right? When we taught bending moment, stresses induced by bending moment is stress X equal to mz over Izz multiplied by Y. Now we are looking at shear force. The shear force will induce what? Shear stress. Okay. Now I want you to watch this. Okay. So over here, I'm drawing a cantilever beam. Okay. So this is our cantilever beam. The cantilever beam. Okay. So I'm going to build this cantilever beams with layers. Okay. Right. And then we have a line over here. Oh, sorry. So from here to here, this is our L, right? And over here, this is our point A, and this is our point B. And the shear force is applied in this direction, right? So this is our shear force, which we call Vy. Okay, and I'm going to include our transformation. Right. So how does the shear failure occur? Right. So if we have a VF over here, okay, then the next one, I'm going to draw the deformation. Pattern. Okay, we're going to draw the deformation pattern. So we have, so again, this is our block or our built-in end. Okay, so our deformation pattern will look like this. Okay, so I'm going to take this. Right, our deformation pattern will look like this. Right. Now, in between these layers, right, you have this going on. Right, so third layer. Right, And you will observe, right? What you observe is these layers that I've drawn, they can slip. Okay, you can call it like a slip plane. Fair enough. Okay. So what you observe down here is the slip is over here. So this is our delta, right? That's our delta. So if now, right? So the delta, right, is due to the slip induced by the shear stress, right? But some of you will say, or yeah, some of us will say, Eugene, but this force is acting perpendicular to the top surface, yes or no? Right? You were telling Eugene, you just drew a right angle at this point, right? Relative to the top surface, it's 90 degrees. So why is it shearing? Right? You ask, why is it shearing? Right? And then the deformation that I've drawn is parallel to the surface. Right? It's confusing now, right? So if you look at this surface over here, right, that I'm highlighting in orange, they are both parallel to our delta. Yes, so it's confusing now. Like, hey, what is this? Is this normal stress or shearing stress, right? Okay, it is shearing stress, and I'll show you why. If we were to pick an element, okay, so we pick an element down here, okay, we pick an element. So I'm going to draw it can be 3D, okay, I'm going to draw a 3D element. Okay, this is a 3D element. Right? So the force, the V, is applying down here. Right? The V is applying down there, right? So when that's the case, the shear stress will behave this way. That's our shear stress. Okay, so this one, so if we were to draw our transformation X, Y, and Z. So over here, this is our shear, right? This is our shear intersecting plane X. The shear stress is in Y direction, and this is shear YX, right? So based on the state of equilibrium, right? I told you guys to remember the shear XY is equal to shear YX, right? So this shear stress and this shear stress are the same magnitude, okay? Does that? So the delta is induced by the shear YX. So this delta is due to shear YX, okay? And it happens to be shear YX is equal to XY. So that is why we classified this as shear failure. Okay, interesting, isn't it? If you look at this, if you look at where I'm highlighting now, you say Eugene, come on, seriously. Where I'm highlighting now, you say, Eugene, isn't this perpendicular? Are we talking about normal stress and shear stress? So if I draw into an element, you realize that yeah, this is shear stress. Okay, so now in this topic, there's only two formulas. I'll write what they are. Okay, so we are going to look at the horizontal shear okay, horizontal shear per unit length. And another term we call it the shear flow. Okay, and the formula is small q is equal to VQ over I. Okay, so I'll highlight this. And the first thing I want you all to remember, okay, this is important. The first thing I want you all to remember is I is a constant. V is also a constant. Q is the variable. And I'll define what they are. Okay, this is a variable. Okay, let's see what they are. So as you know, Q is the shear flow. Right, Q is the shear flow, and the units is in Newton per meter. Okay, V is the shear force, as you guys know. This is in Newton. Okay, and Q, right? Q is defined as the first moment of area, okay, with respect to the centroid axis. The units is in meter cube, and then I'm going to write for you what is the formula Q. So Q is equal to A y bar, where A is the defined area, and this is in meter squared, and y bar is the distance of the defined area centroid to the centroid axis. Don't worry about this, okay? Later on, I'll tell you what they are, and it's in meters, okay? And then the next one, okay? So, oh, sorry, we still have I, okay? So we still have I, okay? So I, sorry, any of you still copying, or you are okay? We're okay? Okay, and then I is defined as the global. Global means the entire, okay? Entire structure and second moment or area. All right, the units will be in meters 4. Okay, so that is the shear flow. Okay, later on I will tell you what the difference between the shear stress and the shear flow. Okay, and then the shear stress, okay, the shear stress for this case is shear xy again is equal to shear YX, and this is equal to VQ